Hi everyone, my name is Mulong Xie. I'm a third-year PhD student in the Australian National University. It is my pleasure to share an interesting work of us, a GUI understanding approach inspired by a psychological theory that states how a human being perceives the world. First of all, please allow me to introduce some background of this work. Nowadays, graphic user interface, also called GUI, is critical in modern software engineering. It is the means for humans to interact with the application and access the underlying functionalities. GUI-related topics are also increasingly trending in the software engineering research, which aim to solve a series of problems in each phase of GUI development, including GUI design, development, and daily use. A majority of these topics attempt to automate certain phases and hence improve productivity and efficiency. One thing in common for these automation tasks is that they all require the GUI understanding in their approach. And in particular, understanding the GUI from video or image is very facilitative or even necessary in many cases. The video GUI understanding requires only images, just like with human being viewing the GUI. It does not demand the underlying metadata and intrusive hacking into the app or device. The very basic visual understanding of GUI is to detect the individual widgets from the GUI image. We apply the state-of-the-art GUI-specific element detector to extract the widgets in our work. However, the detection can only recognize the atomic components in the GUI without knowing the relationship and the overall GUI layout. Knowing the structural information would be practically helpful for many advanced GUI automation tasks. For example, with the GUI layout understanding, the screen reader would better dissect the GUI blocks for navigation. The automatic testing tools would focus on the specific sections and avoid repetitive operations in the same seconds. And the GUI code generation tools would synthesize more modularized and structured code. Therefore, a higher level of GUI understanding is necessary to improve many GUI automation tools. But it can be very challenging to systematically connect the individual GUI widgets into different groups or blocks that fit our human being's perception. So, let's step back and first think about how a human being perceives the world. Here we refer to a well-established psychological theory, Gestalt theory. It states that organisms, including human beings, perceive entire patterns or configurations, not merely individual components. And it formulates multiple principles to review how the perceiving process exactly works. I'd like to use some fun examples to explain them in detail. Here, we have a set of blue circles which are separate and independent, and we don't really see any connection of them yet. But if I draw a bounding box to enclose some of the circles, we would intuitively connect those enclosed circles and perceive them as a group, right? This is called connectedness principle, which states that we perceive elements connected by uniform visual properties as being more related. The form of connection not merely can be a bounding box, but also can be a connecting line that takes the similar effect to make us to group those connected circles together. Next, there are the circles, but if we change the colors of some or the shape of some, we will intuitively tend to group those with same visual properties, which are colors and shapes in this case. This is the similarity principle. In fact, our perception is even more sensitive than we think. For example, even if I do not change any explicit visual property of those circles or bound them with some boxes or lines, we can still perceive them into different groups when I change the replacement. Here we can say, if I move some of the circle a little bit, we tend to perceive them as an independent group separated from other 3 rows. And if I move the next rows up again, we are likely to regard those 2 rows as a group against the other 2 rows. This thought theory names this as proximity principle. The last one is continuity principle. It is more abstract but still understandable. It states that elements arranged in a line or curve are perceived to be more related than others. We can feel this principle in this example, where we tend to see 2 curves composed of circles. As we can see, these principles reveal the way we preserve and group elements into certain patterns, and we hence apply them to form our approach to perceptually group the individual GUI widgets. The use of this principle upon GUI slightly varies because of the specific visual properties of GUI widgets. For connectedness principle, the bounding box that enclose elements are in form of containers containing widgets within them. Let's take a look at the specific example. Here we first take a GUI image. The first step is to detect the widget on it, where the red box denotes text widgets and the green box denotes non-text widgets. And we can feel that we intend to perceive the widgets within the same container as a group, which conforms to the connectedness principle. Next, let's look at the widgets outside the container. And we will realize that we intuitively group those widgets with similar shape or size and spatial placement together. For example, we tend to aggregate the 4 non-text widgets at the bottom into the same group, and same for the text widgets beneath them. We can also look at the clear example, where we observe that all the portfolio photos on the left have the similar shape, area, and element, so they are easily to be regarded as in the same group. So are the bottoms on the right. Note that for those text widgets, we group them by the similarity of the font and elements rather than the shape and area, because the area of text would be inconsistent because of the different content lengths, even for those in the same group and with the same style. To this end, we utilize an unsupervised clustering algorithm, dbScan, to cluster the text and non-text respectively by their value properties. But understandably, some widgets may be clustered multiple times. To resolve this conflict, we assign the widget to a group of the largest similarity with it according to the similarity principle. Then, we apply the proximity principle to further merge the proximate groups with similar members in terms of the number and element. For example, we can observe that the 2 groups at the bottom all have 4 members with the same element. So we further combine them into a large perceptual group. Here we can say the grouping result at this stage. We use the pink bounding box to mark the groups. Also, for the sake of presentation, we denote the pair of the matched items in each group as the subgroups and mark the subgroups in the same color. The above principles are actually quite effective enough to aggregate most individual widgets into perceptual groups, but we can still use the continuity principle to inspect the widget property and correct some detection errors retrospectively. For example, we can say that the detection result in the figure 1 misses a tiny icon at the bottom right because it is too small to be counted as a valid widget by the detector. But after perceptual grouping, the approach can notice that 7 of the 8 subgroups have 2 widgets, where the subgroup at the bottom right has only 1 widget. It then crops the region that may contain the missed wedges according to the wedget area, average size, and relative positions in the other 7 subgroups, and perform the detection again with losing threshold. Also, for the third card in Figure 2, by contrasting the wedges in the 3 cards, the approach can realize that the middle card has text wedges at the top right corner, where the other 2 cards have a non-text wedget at the same relative positions. Based on the continuity principle, our approach reclassifies the top right wedget in the middle card as non-text wedget according to the majority win strategy. There are some realized grouping results of our approach. Here we can say it aggregates the wedges into perceptual groups in a way that fits our human beings' perception as well as the underlying implementation. It can also handle some complicated cases, such as the GUI with a map on it. Other than detecting wedges, this grouping approach can also work with the wedget metadata if the underlying metadata is available. Moreover, our approach can deal with design prototypes as well, which proves its robustness in various situations. In the end, we empirically evaluated the approach upon more than 1K GUI images and found it achieved a promising performance. The detailed experiment can be checked in our original paper. That's all for our interesting psychologically inspired work, and I wish you enjoying this presentation.